And the first speaker is Andrew Holmes. He will talk about, he is from University of Melbourne, and he will talk about the progress in thin film organics and the perovskite solar cells. The floor is yours, please.
Thank you very much. Thank you, Professor Cho. I wanted to share some breaking news with you this morning, thanks to some co-workers here. You know my name is Holmes, and I have my very good friend, Dr. Watson, here with me. And as usual, Dr. Watson will answer any of the questions you might have at the end of the talk. Thank you very much. So I've put a summary of the items I'm going to talk about here, just to introduce something we've all heard about already, thanks to many contributors, the demand for electricity, and what we might obtain through organic photovoltaics, the principles, bulk heterojunction solar cells, and then the desire to make higher efficiency materials, and the new, not so new now, kid on the blocks, the perovskites, and that they have also been very well covered by various members of this conference. And again, the drive towards improvements in efficiency. Can we get away from lead? And how do we talk about large-scale manufacturing, roll-to-roll printed devices? Well, this is where we are with energy consumption now. And you can see that it's dominated by these fossil fuels, and there's a modest contribution from renewables. And the projection for the future, for the year that we're all hoping for, I don't think is very promising. Just look at this in 2025, the projection is that we will have an exceptional increase in wind and PV, a minor, perhaps a few % decline in coal, and an increase in natural gas. So we really got to get our skates on if we're going to do something about this. Now, organic thin film solar cell efficiencies and solar cells in general are measured by their efficiencies, which are determined by the product of three components: the short circuit current, when there's the open circuit voltage, and the fill factor, and these are described on this slide. And just to give you a ballpark figure, this can't be much greater than about 1 volt for organic materials, for reasons I'll show you in a minute. And this is for good devices in the ballpark of 15 to 25. 25 is about the best, it's coming up so far. And it's this one that is the problem child, and that needs to be improved for good device efficiencies. And that is a measure, if you like, of the speed with which the current voltage curve rises with a very high gradient. So it's very rectangular, and then you get a good fill factor. We've seen this slide before already. The devices I want to concentrate on today are those with the open, I have to get a bit closer to my own drawing, here, the closed circle, which are organic cells, and the yellow filled circle, which are perovskite devices. And this is roughly according to the National Renewable Energy Lab, where we are in efficiencies for good devices and ones that have been validated. I will talk about certified, just to illustrate that they have been tested in a lab which is capable of certifying device efficiencies. Now, the bulk heterojunction solar cell has a typical configuration as illustrated on this slide. This is a simplified version, but you have a conducting positive contact anode, indium tin oxide, a conducting polymer, then the active layer, which in early devices was a blend of a donor polymer such as a polythiophene and an electron accepting material such as a fullerene, and then a top contact, which can be a variety of cathode materials, and silver is very common, and because you can print a silver grid which is still transparent. Now, in the early days, people were getting about 2 or 3% efficiencies with this combination of materials. And I want to talk just briefly about our contribution in a solar cell consortium in the state of Victoria in Australia, where we set ourselves target of delivering a 10% efficiency, and that was ambitious at the time for these materials. And the problem is that the devices depend on interfaces, because it's at the interface that the excited state, the excitonic state, resulting from the absorption of a photon, separates into the positive and negative charges. And that needs assistance with a barrier, or barrier is the wrong word, with a break where the charges can separate. So the donor-acceptor interface is where the exciton separates into positive and negative charges, and they don't survive very long in most organic materials until that happens. They survive longer if there's good supramolecular order and good mobility, so they can get to the interface. But the planar interface, as shown here, is not particularly good at providing a maximum number of opportunities for charge separation. And so people always thought that the best thing was to have an interpenetrating network of donor and acceptor materials, so you were increasing the chance of an excited state being able to migrate on this 10 to 30 nanometer scale to an interface where charge separation was assisted by the difference in the HOMO-LUMO gaps of the two materials. And that can also be perhaps more ordered by having a pillared structure like here. So that they have been the motivation for most of the research on thin film heterojunction, that is a donor-acceptor interface material. And a very crude way of estimating what kind of open circuit voltage one is going to arrive at is to look at the occupied level of the donor material, the HOMO, the highest occupied level, which usually has 2 electrons in it, because excitation involves typically absorption of an electron to this lowest unoccupied level, and then, of course, charge migration to the acceptor. And so the difference between this HOMO here and the unoccupied level of the acceptor material gives a crude estimate of the open circuit voltage, but it doesn't tell you how much energy is needed to promote charge separation. So it's reduced by the energy needed to separate the charge at the interface, and that can be fractions of an electron volt, and they lower the open circuit voltage. So that's the challenge. And where should I point this? Towards there? Or there? So I want to talk about the best device we got in that consortium at the time, and that's the configuration is so-called inverted configuration. This is for ultimately for deposition facilitation. It's much easier to work from the bottom up in the way I've drawn this slide. So indium tin oxide, a zinc oxide nanoparticle, which makes that behave as a cathode. The blend of a very good polymer that was designed in the collaboration with the accepting fullerenes, and fullerenes were in the early days the dominant charge accepting material, so a blend of the donor polymer and a derivative of a fullerene, C60, C70 combination. Molybdenum oxide to help the interface with the cathode, with the anode at the top, sorry. So that's the way in which it worked. And that we pretty much made it, although the average efficiency was around 9.6%. But here's the structure of the donor polymer on the left. The fullerene is a hole blocking layer here. That's not the acceptor polymer. It's a hole blocking layer to facilitate negative charge extraction in this direction. And a blend of then the fullerene and the donor polymer. And we reached 10%, but the statistical average was 9.6%. So we made, we thought, the milestone to get paid. So what remains? Well, it remains to get better at everything, really. More efficient materials, so you can improve open circuit voltage, as I said, short circuit current, but the fill factor is the thing one can really work on, and that's related to morphology, it's related to interfaces, and to control in general. And then one would probably want to get away from the fullerenes as a charge accepting material, negative charge accepting material, electron accepting. And ultimately, if this is going to be serious, we're able to manufacture these devices at scale. And lifetimes, of course, are going to be necessary, good lifetimes, in order for these to survive. And we always have to remember, we're talking about competing with a really well-established technology in the marketplace, and that is crystalline silicon. And just to give you a ballpark figure where that is on the rooftop of a typical house, closer probably to the lower number, 15 to 22%. So that's the target we've got to achieve to be competitive. And you can see, therefore, why those perovskites are going to be of great interest. So I need to introduce a few structures which will appear with acronyms under them. And so if you've got any memory, I'm struggling to remember them myself. But electron transport hole blocking layers to facilitate the negative charge going in the right direction have emerged. A copolymer here in which there are amino groups and some electron accepting groups over here, and a copolymer in which these are alkyl ammonium groups with halide counterions. And they've been used quite a lot. That's just to filter the charge direction. And then a non-fullerene acceptor that's emerged is this one here on the right, and you'll see that referred to as Y6 or some derivative with Y in charge in front of it. But you can see this has got lots of electron accepting functional groups, these carbonyl groups, these cyanoalkylidine groups, and this thiodiazole, and again the electron withdrawing groups on this side, and fluorine to pull charge out of the aromatic ring. And on the left I've drawn what's become, just as we talk about privileged catalysts in catalysis, this has become a privileged functional group for the charge donor, the polymer donor group, which is capable of storing positive charge. And this privileged group, benzodithiophene. So typically you see benzodithiophene and then thiophene rings with various substitution patterns. That is a really core group which is given high open circuit voltages. And the other trick is to have then attached to it something that's a little bit more electron withdrawing, and the combination of those two groups in the same polymer means that the gap for excitation is nearer the absorption maximum that's used in silicon, around about 700 nanometers or so. So having those in the same polymer means that the excitation energy is similar to that needed to excite silicon when it absorbs sunlight. So now I'm just going to run through a few examples, and what I felt as I was putting these slides together was, this is now getting complicated both in complex chemical structures and in the subtleties of the way in which the device is being configured. But this is how the numbers have been raised, and it's particularly that fill factor that's making the big difference. So I won't go into the detail of the polymer, but I'll just generally say you'll see here on the left the donor component has got those privileged groups I talked about, and the acceptor component is very similar to that Y6 molecule. Well, there it is on the right. And this is a polymer which could either have the donor molecule on its own, just this part in the left-hand bracket, and the acceptor polymer on the right-hand side is two different components blended, and you'll see that gave in the device 14.6%. When you join them together to make a polymer which has got donor acceptor components in the same polymer, plus a non-fullerene acceptor which is blended with the final mixture. So that's the result here. So this is the copolymer plus 3 weight% of this acceptor blended into it, what we might call a ternary polymer. They managed to reach 15.6%. And this group, Alex Jen's group in Washington, University of Washington, argued that the Y6 is this yellow, filled the interstitial gaps here, the free volume, to give more compact and better order. And remember that supramolecular order improves mobility and therefore will contribute to improved device efficiency. So that's one. They're pretty complex molecules, aren't they? Now, what about this non-fullerene acceptor? What else has been done here? Well, one of the other tricks is to make the acceptor influenced by a third component in which symmetry is broken. And if you look carefully at this, so the donor is pretty similar to the structure I showed you already on the previous slide, but the acceptor consists of a blended mixture of, that's pretty 6 to the Y6 molecule, except with the number of chlorines on these rings, and an acceptor where this ring here is changed from the benzene ring to a heterocycle, and that's blended in a fraction of 20% of the mixture. So it's a one-to-one combination of these two components, donor acceptor, plus a 20% weight contribution here, and 18.2% was the result. And I should say that the explanations that I'm giving you emerged from the investigators having done a range of structural and spectroscopic studies to back up their conclusion. And the kinds of things one can do is fast spectroscopy, which gets you a lot of information on lifetimes of excited states, and then various types of wide-angle scattering and other AFM, surface roughness studies, and so on, to understand morphology. So that's how they come to the conclusion that they reckon that by having this blend of an unsymmetrical acceptor, the balance between charge generation, which influences external quantum efficiency, short circuit current, and charge recombination was better in influencing the open circuit voltage or the loss of the open circuit voltage. So there was some very important computational work. It's important to say that now people are doing computational work. Jean-Luc Bredard's group contributed there to the overall understanding of device performance and efficiency. So you can also play the same game and make the donor molecule unsymmetrical. And you'll see here the asymmetry is the difference in this group versus this group here. And again, a non-fullerene acceptor and 1.4 to 1 blend of these two materials. And they argue that the asymmetric, we call this the 2D side chains because they're not in the, they're in the two-dimensional asymmetry here they're talking about, offers significant control of crystallinity, molecular packing, blend, film morphology, and photodynamics. And again, through a series of studies, this is a group in Wuhan. And here's another ternary blend story where the donors are still very similar to the privileged donors on the left. The main acceptor is this one in the middle, which is a modification of the Y6 molecule. And then there is a contribution of this related acceptor, which is structurally different, in which the absorption wavelength in the 500 to 700 nanometer region contributes to the power efficiency of the device by being able to harness photons that aren't absorbed by the blend on the left. And now we're up to 19% with a certified 18.7% figure. So this means this is the one you believe in terms of reliability and reproducibility. And this is a group from the Chinese Academy of Sciences in Beijing. Now, another driving force in this area is, can we make a polymer which is a combination of the donor and the acceptor all in one block copolymer? And here's an example of that. And this is a Korea University contribution. And you'll see the privileged groups are the same as the ones we've talked about, the left and right, but the donor block copolymer, the N repeat units, and the M repeat units on the right, the acceptor, all in the same material, and the device efficiency of 6.4%, which is about the best I think it's ever been reported for that kind of approach. But you see, it's the fill factor that's pulling it down more than anything else, although these could both go up a bit, because we saw, I think, 20 milliamps per centimeter squared in some of the best devices earlier. So that's where we are with the blended materials. And by the way, the morphology of this material, left and right, is represented by the blue and red color-coded, showing that the polymer self-assembles with all the acceptors stacking up on one side and the donors on the other. Well, in our Victorian consortium, we had set ourselves also being able to prepare A4-sized sheets of printed solar cells. We were still using fairly simple combinations of donor and acceptor materials based on the polythiophene and the fullerene, because this was really a proof of principle that one could do large area deposition. And this is the size of our screen printer, which put the top silver grid electrodes onto the device, which was all deposited by what I'll call roll-to-roll printing, but it's a deposition technique. And here you see the end result of the fully. You can see the grids of the you can see the grid lines of the silver on these things. And this can be cut up into A4 sheets. It was around Christmas time when we did this, and these are sorry, they're all males, the men from the ministry here, and we gave them a Christmas present of a printed solar cell to take home, A4 sheet. Now, the other, since that time, significant contribution in what I'll call larger area devices. So here's a device here of 54 square centimeters. It comes from this group in Wuhan again, and they made modules, subcells, each of an area 6 square centimeters. So the 54 square centimeters obtained by 9 subcells connected in series. And the combination is a PET silver grid, silver nanowire, and then a polyethylene imine zinc coating, which would make that then the cathode, and then the donor polymer on the left, the fullerene non-acceptor on the right. And they did deposition, first of all, by spin coating on glass, which is not a large-scale manufacturing technique, the combination of the PET silver grid with zinc nanowires and polyethylene imine. They put that on glass, then they assembled the remaining parts of the cell from the right to left onto a flexible polymer device, and then they printed the stuff on glass by putting it into water and floating it off on a layer of polystyrene sulfonate, sulfonate sodium salt. And that exfoliated layer was then transferred onto the final substrate to put the top electrode configuration. The problem with these device printing is if you build this device up, as I showed in the example we had, you can't have any serious thermal treatment process to deposit the silver grid onto the top. You have to have it pretty much because the morphology, the PET, the polymer, the plastic, these aren't polymer bottles we've got here, but the plastic drink bottles that you buy, that's PET, that can't survive high temperature treatment. So you have to have a final process that is low temperature or lower temperature. And this way of floating it off and transfer printing it is one way around it. I'll show you an even more impressive alternative approach from CSIRO, the Government National Lab in Australia, our partners in all our solar cell consortium work, in a minute. But before that, I'm going to move now to the perovskites. And this was they were explored first of all, and we all know what they are now, thanks to the many informative talks we've had. They were first explored by Miyashita in Japan, but it was Henry Snaith in Oxford who really surprised everyone by developing at first a vapor-deposited combination, and here is the configuration. And the important thing is there's a hole blocking layer here, but the perovskite layer here, and then an organic material to take the negative charge, the positive charge, out. So it's the other way around, isn't it? So, but anyhow, you need a perovskite and an organic hole transporter to get charge separation. And you see, this is amazing. It was well above in 2013 the best device. Our 10% was, I think, around about the best device at that time. So what are the challenges to get on? Because this is clearly something that everyone's got quite excited about. Stability. Perovskites aren't stable, neither are the organic materials without protection against photooxidation. So you need to encapsulate all these devices. And it turns out that one of the most expensive components is the encapsulation material in this work. So encapsulation, because perovskites certainly don't like water, and there are other reasons that help them break down. And then there's a lot of understanding now, which the perovskite people in the audience will understand far better than I do, about the issues of roughness of the layer, which is related to the way in which it's deposited and how it crystallizes, and the interfacial interactions. Interfacial interactions, as you've heard, really important for charge extraction. And then, if one's going to go on, large area deposition, and I'll finish off with talking about tandem devices. So this slide taken from this review article shows the typical deposition techniques: blade coating, which the illustration is simply a blade drawing across a solution which has been deposited. Doctor blade, slot dye, where the solution comes through the blade which is drawn across the material. Spraying, again, it's obviously a raster process. Spin coating, which is where you simply put the device onto a flat disk and spin it at a quite high speed, not good for manufacturing. And inkjet printing, which you all know about. Now I have a slide here which gives a rough idea of what kinds of efficiencies one gets with what kind of techniques over the years on perovskites. And really one's concentrating on numbers up here in terms of progress and efficiency. And small devices have given pretty good numbers in the 20%, and larger areas, they're not quite as efficient. You see they're more nudging towards the 15. There's one or two that are getting up there. And I'll just talk about some examples of high efficiencies, and again, the complexities that have emerged in having to reach those efficiencies. In our own case, in our own consortium, the best result we obtained in 2015 was through slot dye coating of a perovskite onto a glass substrate, not a flexible substrate. Here you see the image of the slot dye coating. And I'll show you the assembly, but here you see the components. We had zinc oxide, we had the perovskite, methyl ammonium, lead iodide, and poly-3-hexylthiophene as that P donor material. And this is the way in which it was done. Zinc nanoparticles were slot dye coated onto the ITO glass and annealed at high temperature, relatively high temperature, 120. Then lead iodide was coated from DMF, followed by vapor annealing in a chamber. Then the methyl ammonium iodide was coated onto the lead iodide film at 70 degrees Celsius. And finally, the poly-3-hexylthiophene was deposited from dichlorobenzene with lithium trifluoride, which turns out to be quite a good radical source, actually, but it's often used in transport of charge onto the perovskite, and then silver vacuum deposited onto that. And that showed quite a good efficiency for the time. 10% was pretty good for that kind of fairly larger area device than not large, but larger area device. So that was the progress. Well, since then, in device fabrication, these are largely smaller devices, often just 1 square centimeter in area, so it's postage stamp size, if you like. Some tricks have been played. This group described how they, a Korean group, how they modified the negative contact here by titania deposition and then doping that titania with a coherent layer of the formidinium lead triiodide carrying chloride ions. So that just, as they say, enhanced the charge extraction and transport from the perovskite into the electrode. And it also removed interfacial defects. And then the rest of the construction is conventional, if I can use that word, perovskite, formidinium lead triiodide, and the organic hole transporting material is a molecule called spirometad. It's a spirocyclic molecule with amino groups on it. It's still to be beaten as the best material in this area for perovskites. I'll show its structure in a minute. And they're 25.5% certified. So it's starting to get quite seriously good numbers for a small device. And the spirometad is this structure here on the right. Now, I've summarized some other results here because one can go through it and it gets a bit tedious going through it, but some tricks to be played. Surface engineering, using aminomethylpyridine, and all the structures are there. I won't go through them. 25%. This is an interesting one because lead iodide is one of the outcomes of instability of the lead alkyl ammonium or other lead perovskites. And this trick was to convert it into an inactive secondary phase with rubidium. And that device showed a nice efficiency, 24.1. And I haven't got these certified, so you may find it not really as good as they state their lab results rather than certified results. And then actually doping this spiro material with radical materials to provide whole polarons and increase conductivity and work function and modify energetics of the polarons using ionic salts, 25%. What else has been done? Well, I'd like to talk here about tandem solar cells for a minute. Now, this is used in sophisticated silicon solar cell science as well, but as described on the slide, silicon absorbs quite long wavelength regions of the solar spectrum, around the 650 and 700 being the main absorption. There are other absorptions. But the idea is that anything that is excited with a shorter wavelength excites the excitonic state in silicon beyond the level where charge separation can occur, so it's lost as heat. And so the idea, which is well developed in this area, is to have in front of the silicon cell a solar cell capable of absorbing the short wavelength light, and then to couple these in tandem to get more energy from the solar spectrum. And the Swiss center at EPFL in Lausanne developed a tandem perovskite on a 1 square centimeter planarized silicon surface and obtained a 30.93% efficiency, which has been validated. So that's a fairly impressive result for a small device. Now, I want to talk about the CSIRO work, which, as I said, the CSIRO is the Australian Government National Research Lab, covers the whole spectrum of science, not just solar cells, from food and agriculture through to human health care and materials in between. And I think they've done quite well here because they've again used the trick of depositing the silver electrode in a second stage by first of all assembling it by coating silver paste onto a flexible substrate which is coated with a release layer, a silicone release layer. So first the silver is deposited, then dried by solvent evaporation, then a carbon paste is deposited on that and dried by evaporation, and then it's transferred to the partially assembled solar cell by this deposition technique, which is a reverse gravure technique in which rollers are turning clockwise and counterclockwise against each other, and the printed electrode that I've described there is released onto the surface of the partially assembled solar cell under the pressure of the roll-to-roll calendar press printing process. Now, the rest of the solar cell is again reverse gravure deposition of tin oxide, slot die coating of the perovskite, and then slot die coating of the spirocyclic whole transport material. And there is a mild thermal process involved that. And then this calendar press assembly of the top electrode gives you a device which has this configuration with the printed silver on top. And there they achieved, on a small device, an efficiency of 16.7%. And you see, there it is, the limiting factor is again this fill factor. And I think that's going to be the thing that printing deposition or deposition from solution has to overcome. And they produced a 10 by 10 square centimeter module with a 12% efficiency. And I think these have been validated. So I think that's really quite an impressive result. And then a comparable result was a flexible all-perovskite tandem cell with a small area, not a large area, has been obtained by this group, and they used two hole selective materials based on these carbazole structures to give a self-assembled monolayer, and they bridge the perovskite with a low-temperature processed nickel oxide nanocrystal film. And then the whole selective contact mitigates interfacial recombination and facilitates whole extraction. And so it's quite a complex structure again, but here we see it. Basically, the active layer is a combination of the formidinium and the cesium perovskites, but they use C60 and bathocuprine to deal with the charge extraction. So that's an impressive result, 24.4%. And then ultimately we have to think, how do we get away from lead? Because the EU bans devices with more than 0.1% lead, and the lead-based perovskites typically contains up to 10 weight percent lead. And I think those who live in Europe say that this will never be allowed unless you get rid of lead. So tin is the most suitable alternative that's come to mind so far. The problem with tin, though, is it's even more easily oxidized to tin 4, and that produces p-type doping and higher background carrier density. And then there are vacancies that arise through the weak bonding energy of these elements, and fast crystallization promotes pinholes and rough surface and a higher charge carrier recombination rate. All these results in a large loss in open circuit voltage of more than 0.8 electron volts. That's a lot to give away through morphology. But the best result, I think, that's been achieved with a tin halide perovskite is one that used triethyl ammonium iodide and ethylene diamine to coordinate uncoordinated tin and suppress charge carrier recombination at the surface. And they also used ethylene diamine to passivate the surface, as I've just mentioned. And that combination, I'll just talk to the result, the optimum result. The optimum result is EAO.1 EDA, which is the combination there, which X is 0.1 in this formula of the formidinium combined with that 0.1 EDA tin iodide in the perovskite layer. And again, bathocuprine is involved and silver. And that achieved 13.24%. Now that's not bad for tin. That shows tin has real promise, I think, because it wasn't long ago that we were seeing 2 or 3% efficiencies with tin-based devices. I just finally want to move to the work of the Heliotech company in Dresden, and they promoted the advantages of solar in Dresden by pointing to the fact that the carbon footprint on this scale is 8, and look at the carbon footprint compared with crystalline silicon and all the other sources of energy that we use. It's certainly only beaten by hydroelectricity. Now, I don't have a lot of detail of their material, but I have some photos taken from their web page. And this is the fact that they've installed a 476 square meter organic solar cell module. And the organic materials are not polymers, they're molecular materials in Berlin with an 18 kilowatt capacity, 546 films. So that's an installation that's in Berlin, in place, and they don't talk about efficiencies, but let me just summarize now what I've presented to you, that the best single bulk heterojunction cells, 19%, the best polymer solar cell, single polymer solar cell, 6.4%, the best large area flexible bulk heterojunction module is 13%, the best solution deposited peroxide cell, 25.5%, the best large area perovskite module, 12%, the best lead-free perovskite, 13.24%, and the best tandem peroxide on silicon, 30.93%. And as I said, I don't have the efficiencies for Heliotech, but my guess is, knowing what we do about the best organic materials, it won't be much. It'll be between 10 to 15%. Their process, by the way, for deposition is roll-to-roll vacuum deposition of materials, because molecular materials can be sublimed and the electrodes can be deposited in the vapor phase. So I want to acknowledge the consortium that worked in Victoria with this slide, which is, what shall I call now, more historical, but these are the groups and people with whom we worked, and the international collaborators as well. And again, I'd like to thank IWAM for inviting me to talk at this meeting, and thank you for your attention.
Thank you very much. You can stay on the stage.
Dr. Watson is now going to take over.
Yeah,
Thanks for such an informative talk across all the different solar cells. Really interesting. So you really highlighted actually the complexity of making the devices. So many layers and all, different nanostructure and all that. And you also talked about the lifting off the organic materials and then redepositing. So what was you were saying that you have to have a high temperature process after that. That wasn't just for putting the silver on it. What was that?
Well, you do have to thermally process the silver because it's got a solvent-based deposition technique. For the lift-off technique, you avoid all that. But
yeah, but I mean, the problem was the high temperature of the silver bit to anneal it to sort of get good contacts or something. Is that it?
Well, first of all, removing solvent at a temperature that doesn't change the morphology of what's already there, and also the PET, which has a can't remember the word now, but the deformation temperature around 100 Celsius before it starts to stretch.
Right. And so my other question is, where do you actually think the perovskite solar cells will be used in the future?
Well, I think that some people outside Europe think that people will live with a device that has 10 weight %, providing it's... I understand it's quite hard to recycle silicon solar cells at the moment. It's causing a problem, but provided those aspects can be captured, recycling of lead perovskites in some countries might be quite acceptable, but not in Europe. So if you want the European market, which of course is pretty big, you're going to have to probably work on tin, which is not intoxic, but it's less toxic.
Mm-hmm. Thank you. Thanks.
Maybe get the student.
Hi, wonderful talk. I was curious, when you are printing the lead iodide, you print the lead iodide, let it dry, and then add the methyl ammonium iodide.
That's what they did in that project, yes.
So how do you, I guess, induce the actual formation of the perovskite structure so you're not left over with any lead iodide?
I think that could well be an issue that hadn't been solved at that time. Okay. And I think now, in the later work, they were depositing a preformed alkyl-ammonium perovskite.
Second question. With these organic cells, how complex, these seem like very complex monomer units. How do you actually, are they feasible to produce on a large enough industrial size scale to where you can actually make enough to make a dent in our energy?
I think they're complex, but that they're not quite as complex as pharmaceuticals, but I think they can be. There's fairly small amounts used on each device. So I think it's a pity that they've become so complex because we were selling the work on the fact that these were readily available, large-scale bulk materials that we could easily use, and that was certainly the case with the thiophene, polythiophene, and the fullerenes. We were producing by continuous flow, 10, 15 grams a day, and just in a small flow device of the fullerene used, the PCBM device material. But I think manufacture already, you can look at the catalog, most of the nice results now are made by people who buy their materials from Lumtech or a related company in China. And you can look at the price for they're probably similar to small chemical device prices, but I think they can be scaled up. Yeah.
Thank you.
Thank you.
Thank you. Last question, Tony.
Thank you so much, Andrew. That's a fantastic survey of what's going on in this area. Looking at the perovskite ones and the high-performing ones are incredibly complex in the chemical sense, do you think these are going to be cost-effective against silicon going forward?
I think that's the question. Everyone who gets involved in starting a new technology should ask themselves every day, because as we learned with other devices, the device to beat is the one already in the marketplace. And I think that's the only thing probably that will work in favor of the materials science, is the organic materials in general and perovskites in general, is the desire to get away from the energy-intensive manufacture of silicon devices, and that may require legislation. I don't know.
Yeah.
So, but I think the marketplace has to be competitive. Now, I think we're seeing that nearly all the problems are soluble. Interestingly enough, in the printed devices we had, the most complex thing about device efficiency was alignment of the printer in deposition. And that's an engineering problem, and we were doing it as amateurs, but just to deviate, if I've got time or are you in a hurry, deviate quickly, Australian polymer banknotes are printed, and they're printed in Britain as well now, and they have very sophisticated alignment feedback devices that can control that. We didn't have access to that, but I think that printing will become efficient and cheap, but beating silicon, I'm not going to put my money into that product yet.
Thanks.
Okay.
Thank you very much.
Thank you very much
Thank
for
you.
the excellent talk.